Okay, this podcast will talk about IPv6 addressing, which is a layer 3 concept. IPv6 addressing architecture was originally defined in RFC 1884, was updated by the following RFCs. Main things we want to know about IPv6 addressing we'll cover. Mainly IPv6 address is 128 bits long, which is 4 times longer than an IPv4 address. There are 3 types of addresses: unicast, anycast, and multicast. Unicast is what we're used to one-to-one with our normal IPv4 addresses, where you're sending from one host to one destination. Anycast is a new concept with IPv6 addresses. There can be multiple anycast addresses spread out geographically, and with an anycast address, the traffic is delivered to the closest address. So that's to help get to the closest place to get services. And a multicast address is, again, one packet from one source to multiple destinations. If you'll notice, there is no broadcast address with IPv6, which was something we have with IPv4. However, there is an all nodes multicast address, so it's the same thing as broadcast, it just has a different name. But technically speaking, there is no broadcast address for IPv6. And with IPv6, the addresses are assigned to the interface, not the node. So you should be aware by now that it's pretty common for a computer or a router to have more than one network interface. So before we called it the host address with IPv4, but it wasn't really the host address because the host could have multiple addresses. So with IPv6, we made the distinction, and now the addresses are assigned to interfaces, not the nodes. So IPv6 addresses are written in hexadecimal colon notation. As you see above, we have X colon X colon X colon. So there's 8 groups of characters, where the X's are 1 to 4 hexadecimal digits, and of the 8, 16-bit pieces of information. So we have some examples: A, B, C, D, colon, EF, 0, 1, colon, blah, blah, blah. So that's a full IPv6 address with all the characters filled in. The second example, it starts with 2001. You'll notice some things. You should notice some things about it. Some of the leading zeros have been omitted. So in the second group, we have DB8. Well, that really breaks out to 0 DB8. And then we have 008. Well, that 8 is really 0008. And then we have 800. That's really 0800. So we can get rid of the leading zeros in most cases. We can also do further abbreviation. If there are many groups of zeros, we can replace those with colon colon. So if we look at these examples, we have split into 2 parts: the examples and then the shortened representation. We have 2001 colon DB8 colon 0 colon 0 colon 8 colon 800 200C 417A. If we look down at the first shortened representation, you see that after the DB8 we have colon colon, and that has taken the place of the 2 groups of zeros. So the question might be, how do you know how many zeros need to go back there? Well, you have to have 8 groups. So if you have 1, 2, 3, 4, 5, 6 groups present, that means you need 2 groups of zeros to replace those colon colons to get back to the full length. The next example, we have FF01, some zeros, and then 101, and we shorten that to FF01 colon colon 101. Again, how many zeros need to go back in there? Well, we have 2 groups present, so that means if we wanted to write it out, we would need 6 groups of zeros. The IPv6 loopback address is all zeros and a 1. It can be written as colon colon 1, and the unspecified address, that's the address we use if we don't know our address or don't have an address. That's all zeros, and that can be written as just colon colon. So you can only replace 1 group of zeros with a colon colon. So if we look at the example, we have 2001 DB80080008. The first example under that is not correct. We have 2 groups of two groups of 2 colons, and that's not correct because we don't know how we can put that back together. Does that mean there's 1 group, 1 0 at the first double colon and 3 zeros at the second double colon, or does that mean there's 2 groups of zeros at the first one and 2 groups at the second one? or is there 3 groups at the first one and 3 groups at the second, and 1 group at the second one? We don't know that, so that's not a legal substitution to have 2 sets of colons. So the rule is normally you normally want to replace the longest continuous group of zeros with 2 colons, or the first one if there's 2 groups. So if we look at our example, we have 2001. The second example, 2001 DB8 : 8000417A. So that first group got replaced with double colons, and now we know there's 6 groups of letters and numbers, so that we can know that there needs to be 2 groups of zeros to replace that. This would be a good time for me to point out that these are hexadecimal characters, so if you're ever asked which of the following are valid IPv6 addresses, you might want to make sure there are no non-hexadecimal characters in that IP address. So we can write IPv6 prefixes like we would write IPv4 prefixes, but no, not really, because we can just drop off a bunch of it using the 2 colon notation. So here's a way we would write the 60-bit prefix shown. We can write the whole thing out, including all the zeros to the end of the address, /60. That's the first example. We can remove the leading zeros from each group. So we have 2001 0DB8 : we use that to replace that group of zeros, the first group of zeros, and then we have individual zeros at the end. That's a legal representation. And then we can use the : to replace all the zeros at the end, and we have 2001 0DB8 0CD30 : /60. And that's the most common representation you'll see for writing an IPv6 prefix, the 2 colons at the end to replace all of the zeros in the host portion. So here are some examples of bad ways of writing the prefix. The first one, we don't have : at the end. We can drop the zeros, but we have to put the : if we want to do that. The second example, we have the : in the middle, but we don't have anything at the end of the address to represent the host portion. So once you put the zeros back into that address, you end up with the 2001 0DB8 with all the zeros and then CD30. So that's not what we're looking for. So that's not a valid representation of that prefix length. And then the same thing for the bottom one, except we just put the : in the different place. No, yeah, so that's bad, because that's bad for 2 reasons. One, we put the : in the same place, which caused the same problem, but then we dropped off this last bit of the I don't know what you call it. What do you call I don't want to call it an octet, because there's 16 of them. Group of numbers. So the entire group is CD30. You can't abbreviate a prefix in the middle of the CD30. So you have to have this trailing digit. So you need that 0 on there. So that's why that's not permissible. And then with the 2 zeros, it breaks out to the wrong thing. So we have 3 different kinds of unicast addresses. We have global unicast addresses. These are the public IPs that are routable across the internet. We have this idea of site local unicast addresses, which these are equivalent to the private IPs we have with IPv4. The latest RFC says that site local addresses are deprecated, so I'm not sure what the state of those are. Then we have the link local address. Every interface will automatically generate its own link local address, so that it can use that locally to communicate via IPv6 to try to find a router and that kind of stuff. So if you look at your IPv6 host, it'll automatically have a link local address, and they usually start with like FE80 or something like that. So here's how we can identify the different types of addresses. Unspecified address is all zeros. The loopback address is all zeros followed by 1. A multicast address will start with 8 bits of 1, and a link local address will start with the first 10 bits of 11111, 8 ones, and then there's that 6 ones. How many ones is that? 1, 2, I think it's 7. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 ones, a 0, and then 1 0, which works out to be FE80. And then everything else not mentioned is a global unicast address. So we have the same idea with IPv6 addressing, that we have a network part and then the host part, or in the IPv6 case, the interface part. We can also break that down to where the host part becomes a global routing prefix, and then a subnet ID, and then the interface ID. So the idea of that is like the global routing prefix will get it to your company, and then once it gets to your company, the subnet ID will get it to the particular LAN it needs to get to, which is very similar concepts to what we're used to with subnetting IPv4. You know, we get an entire block of addresses routed to our company, and then once it gets there, we need to break it down and send it to different networks within our company. How do you assign IPv6 addresses? Well, you can do static assignment of IPv6 addresses. After a few hours in the lab, you'll probably decide that's a bad idea because typing IPv6 addresses is kind of tedious. DHCPv6 will be stateful auto configuration. This is where you have a DHCPv6 server that listens for requests and hands out addresses and keeps track of the leases that are handed out to each host. And then we have the idea of stateless auto configuration with IPv6. With stateless auto configuration, a host will come up and send out a router solicitation, right? The router will send back the information the host needs to join the network in the form of a router advertisement, and then the host can automatically build its IPv6 address by taking that information the router sends back, which includes the prefix and the prefix length and some other stuff, and then join the network. So that's a way that host can automatically stateless auto configure their IPv6 addresses. I think those are the high points of IPv6 addressing that I wanted to cover. If you have any questions, put them on the discussion board or bring them to class.